So it was the example that I gave, where there was a two-path coupled at different chemical potential, and then I was looking how much of net particle flow moved from one side to the other, and then I said that there was this large deviation form. So Qt is the total number of particle flow from left to the right. So this has this following large deviation form, where L is the system length, and this goes as minus T by L phi of J. And then there was this symmetry relation. That was phi of minus J minus phi of J. So here I wrote something wrong. I wrote something 1 over mu A, but it's something, it would be mu A minus mu B. Okay? So this is the part where I wrote something. Please correct in your note. Okay, so what else did I tell you yesterday? So I started with Langevin equation. So Langevin equation was just like writing Newton's equation in presence of the noise. And then I went to overdamped limit. Where I took the inertial term to be negligible, and then the equation become Q dot equal to FQ divided by gamma plus eta. This is now just a rescaled eta, and there was this autocorrelation function, which was simply twice Kb temperature by gamma delta T minus T prime. And then, so from now onwards, I will denote this as sigma, okay, the noise strength. Then I wanted to study large deviation in the small noise limit, weak noise limit. So for the small parameter, as a small parameter, I put a prefactor epsilon to this sigma, which is small. Okay. Then I went to a path integral formalism, where I said that if I want to look at a particular evolution, so I want to see the probability to be at Qf at capital time t. So now onwards, capital T would denote this time, not temperature. Started at Q0 at 0. This has a path integral formulation. This goes as minus 1 over epsilon, and then there is an action, which is a functional of the trajectories. So it's, the picture was, let's look in the time direction, there is Q, and it's evolving. Starting from Q0 at time t, I'm at Qf. Okay? So this says that there are many such trajectories, and each one has a probability weight as exponential of this action. And the action, it has a Lagrangian form. So Q of t, it's just like in classical mechanics. T, L, function of Q and Q dot. And we had L, Q, Q dot is equal to, it's a Gaussian, so F divided by gamma whole square by twice sigma. Okay? And then I said if I want to look at the large deviation of this probability, that means I want to look at a formula where I want to see Qf, this probability, Q0, and I wanted to see a large deviation form this sort. So W, T, Qf, because it's a function of both Qf and Q0. Then this is nothing but the minimal action that will come from this path integral, which only says that for very small epsilon, I can do a saddle point, Okay? And there is one path which contributes the most, and this corresponds to the path of least action. Okay? So the W was S, so minimum over S over all possible trajectories. Okay? And then, as an example, we took the case for where FQ was just a force due to a potential. The potential was UQ. And then I demonstrated to you how to calculate this quantity. Okay? And we derived the formula that we expect, that this function at the large T limit, this simply becomes 1 over epsilon phi of QF. It forgets about its initial position. And this is nothing but, phi is nothing but U over QF divided by KBT. So this was the temperature. Okay? Okay, so that was done in the Lagrangian picture. But just like in classical mechanics, there's a Hamiltonian picture. Okay? So now today I will just talk briefly about that, and I will solve the exactly same problem, the repetitive exercise. But this is useful because when I go into more interacting particle systems, sometimes the Lagrangian picture is easy to solve, and sometimes the Hamiltonian picture is easy to solve. So let's just now go into the Hamiltonian picture. So you could recall from classical mechanics that one could just go from the Lagrangian to Hamiltonian picture by just the Legendre transform. So I go so here the Hamiltonian, so there is the momenta coordinate. So it's a function of two variables, and this is PQ dot minus Lagrangian Q dot, where P is simply del L del Q dot. Okay. Now if you just do this exercise, it's very simple to do. You'll just end up H PQ is simply sigma by 2 P square plus P times F of Q divided by gamma. So given this Lagrangian, I have this Hamiltonian, okay? And that all started from this overdamped Langevin equation. Okay? So now if I want to look at all these parts, okay? So now the action that is the same picture, just the action is now written in a different form. So now I'm just going to write this again. I want to look at QF at T, Q0 at 0. So now I have two variables, P and Q. Now this is 1 over epsilon S. Now it's a function of two variables, P and Q, the momenta and the position coordinate. And now this S is simply dt P Q dot minus H. So this all just, you can get it with standard classical mechanics, okay, from the textbook examples. So what now the problem reduces is now the same thing, that now I'm going to, if I want to calculate this large deviation function, I need to find the minimal action again, but now I have to minimize over two different variables. Okay? So Q and T, P and Q. Okay? So now this way, so last time I said that the minimal actions, the optimal trajectory, that's the least action path, satisfies the Lagrange's equation. But now it's simply would satisfy Hamilton's equation, which is very simple to show, just like in classical mechanics. So this we call is least action path. This is also sometimes referred as optimal path, because this is the path which contributes most in seeing the probability. Okay? This is the most probable path to see that particular final position. So sometimes I would refer either least action or the optimal path. So this is nothing but just the solution of Hamilton's equation. and Q dot equal to del H, del P. Okay. So there's this two coupled equations. So I need two boundary conditions. So one is, so in the problem when I'm studying this one, where I'm fixing my initial position and final position, that gives me the two boundary conditions. So for that particular problem, my boundary conditions are at Q at 0, is simply Q0, and Q at capital T is Q of F. Okay? So all just straightforward. Okay? So what I'm now going to do, do the same exercise to derive this large deviation function for the case where the force is due to a potential. Okay? And I'll again use this concept of time reversibility, and you will see that the solution comes out very easily. Okay? So now let's just write down. So how does these two equations look like for this Hamiltonian? It's a very simple exercise. You'd find that P dot is equal to minus P F prime of Q divided by gamma, and Q dot is equal to sigma P plus FQ by gamma. Okay? Now it's instructive to actually look at this equation, okay, and compare that with the original overdamped Langevin equation. So let me just write that part again here. So this is the starting stochastic differential equation. So this is, there was an eta part, and then there was FQ by gamma. So one should look at this physical picture. So what's happening? So if I'm in a potential well, and I'm starting, let's say, at the minima, so what would happen that if I want to see some position in the uphill at some point, it is less likely. Okay? So for that event to happen, there's the noise path that's coming in this equation. It has a particular history, which will kick my particle and push it over here. So I need a certain noise history to have this unlikely path. Okay? So the probability is essentially the probability of that noise history. Okay? And if you compare these two equations, you see that P almost plays the role of that noise term. Okay? So just keep in mind, so it's something like a P is the driving force, the noise term, and which is pushing, and that P also depends on where in the trajectory you are. Just to keep in mind. Okay. Okay. So how does one solve this? So what I now need to do, so let's just, it's not necessary. So I have this equation, and I'm solving this problem where I want to start at the minima, which is Q star. I want to go to QF. Okay. So now the problem reduces that I start at Q star at minus infinity, just like yesterday. So my boundary condition would simply now change. So the noise is already there. So noise part, what does the noise part mean? If you have many different, so for particular noise realization, one would get a particular path. Okay? And if you have another noise realization, you'd get a different path. Now, if you want to see a particular event that's happening, that will come due to a particular noise realization. And the action gives you the measure for the probability of that. And when I'm looking at this least action path, it's telling me the most probable trajectory, which is contributing to seeing that atypical event. So P is like the noise term displayed for that particular trajectory to happen. So for that event to happen, that start from Q star, go to QF, there are many such trajectories. Okay? But only one of them, at least in this simple example, which contributes the most. And that's the one which decides in the epsilon zero limit, the large deviation function. Okay? Precisely. So that's the comment I'm going to. Precisely, yeah, yeah. So it's essentially, so maybe I wanted to make that comment. So this action formalism has appeared in many other places. So one approach is called this Martin-Sigia-Rose deterministic formalism. So I kind of forgot to write it. You can look it up. So this is called Martin-Sigia-Rose, and then independently by deterministic. Formalism. And the P is just the response field for that particular piece. Sorry? Minus infinity. Okay, so now, okay, so I'll come back. Let me just finish this first. So this P is known as response. Okay. And there are papers which I don't have the reference, but if you search in Google, you will find it. Okay, so let's come back to the original problem. So what I want to solve, that I want to start at this minimal position at minus infinity. Then I want to be at this position at time t equal to 0. Okay? So my boundary conditions becomes q at minus infinity, it is at q star, and q at 0 is qf. Okay? So all I need to do is to solve this equation with this boundary condition for any general f, take that solution, plug it into this formula here, and that should give me the large deviation function. Okay, so now you already know that what does the solution of this would look like. So yesterday I told you, yeah. So P is called a response field in Martin-Sigia-Rose. There's a reason for it. Let's not get into that, right? Okay, so the solution for this, you could easily guess. It's because I told you that there is a time reversible symmetry in equilibrium. So this path has to be exactly the same as the system would have taken if I started here and went back. Okay. So for the time reverse path, so if I had write QR dot, it would have been the FQ, so time reverse path, by gamma. So let's call this time like this. Okay. Okay. So because what happens there is that it just slides downhill. Okay? So the most likely profile is just the noiseless solution. Okay? So now if you from here, you just go from tau to minus t, you know that the solution for this forward process, it should be simply minus f of q divided by gamma. Okay? So if I just use that f thing, so you will very easily convince yourself, and I can check. So the solution becomes the q dot equal to minus fq by gamma. I'm not solving this equation, but I know that the forward trajectory would satisfy this equation, and the equation for P now simply reduces to minus twice FQ by gamma. So this you just check by simple algebra. Okay? Now one statement which is important, and it will be used later on in some other problems, I just want you to check that if I choose this solution, and put it in the formula for the Hamiltonian, you'll just find that the Hamiltonian becomes 0. Which means that for this optimal path, the paths are decided by this h equal to 0. Okay? So just check that for this optimal path, this is P, Q, is simply 0. I'll give a reason later on. This comes in terms of Hamilton-Jacobi equation. But this is something that one should keep in mind. Okay? Now that I have all these kind of roughly the solution, I haven't solved this one. But just using that, I can get back the formula for the large deviation function here. how do we do that? It's very simple. So my large deviation function now, the QF, is simply the minimal of this S of P and Q, okay, which, if I just write, is simply minus infinity to 0, then dt. I had P Q dot term that came from the action. Yeah. Yeah. Yes. So, of course, one could solve it explicitly, but I'm just using this property, the time reversibility in equilibrium, which says that if in the forward process I have an optimal path, it would be the same optimal path if I had looked at the time reverse process which was going downhill. So for that time reverse process, it would have been just QR, yeah. Exactly, and you just changed it, yeah. And you know now that this actually ensures that this solution will satisfy also these boundary conditions. Because you know that for relaxation, it would have satisfied the boundary. Okay, so now you just see this part, the action, was PQ dot minus H. And I told you, just you can check that the H is 0 by simply substituting these results. Okay. So this is now becomes this one. So this is nothing but minus infinity to 0 dt. So P, I just use the result here. So twice F of Q by gamma sigma times Q dot. Okay. So what I'm now going to just do, take this path, I'm assuming the sigma is constant right now. So that's the problem we are addressing. So now I'm just going to take twice by gamma sigma out. Now I have Q dot dt, I'll simply write as dq. So that means at minus infinity it was at Q star, it is now at Q0. Okay. So Q dot dt I wrote as dq. F is nothing but minus of del u, del q, and so this becomes plus. Okay. Now we are almost there. So the result that you'll finally get is twice by gamma sigma q of qf. Sorry, it's depends. So it's not q0. Sorry, it's qf. I'm going to be at the final point. So qf minus u of q star. Okay, and then using this fluctuation dissipation relation, I told you that this gamma and sigma are related, and it will simply reduce to 1 over kbt. The usual result as one expects. Okay, so this was quite a simple exercise. Yes, true. You're absolutely right. So that's why I'm looking at the problem where I started at minus infinity and I'm at 0. Okay, so right, because of just your question, let me give one example. So here so far I kind of solved the problem using certain simple properties. Let me give you just one example where you can explicitly solve from one particular time to the other time, and then you take t tends to infinity. So this I will not solve here, but I will just give you roughly the picture what happened. So can I erase this part now? Yeah, I just wanted to start from here. So this part I want to erase. Okay, so this is an example now I'm giving which you can really explicitly solve, and it's a very simple example, but it's good to sometimes solve really simple examples to get an idea what's happening. So I'm now going to consider if just this simple, this potential, just the bookkeeping potential. So here now the minima is at 0, so my Q star is simply 0. And I'm going to now choose the gamma being 1 in the Langevin equation. Okay. So now, what the problem I want to address is this, that if you start at, let's say, minus capital T, and one starts at this Q star. Okay, so, sorry, I just take back one. So now what I'm going to do, rather than starting at Q star, which is minima, I'm going to start at some other point. So let's call this Q0. And I want to be at some other point, at QF. So this, I'm going to start at minus T. Okay. And this, I want to be at time 0. Okay. And then I want to look at for this probability. What I want you to do is to solve this problem with the very same formalism. It's very simple to write down. In this case, you can actually solve this optimal set of equations for this particular profile and show that the optimal paths simply look. Let me just write down the formula. It's long, but you can actually check it later on. So 1 minus T plus T this, of course, you can solve quite easily. But just to be consistent, let me just write. The solution for PT be twice QF e to the power small t sigma 1 minus twice t minus twice. And if I put it in the action, the corresponding one, so the minimal action, so S min, would simply be QF minus Q0, the place where I started, e to the power minus capital T, whole square, divided by sigma 1 minus 2 minus 2. Okay, so, okay, let me give you some time to write down. But what we really want to see, how these profiles look like. So I started, the time axis, I want to be at 0, start at minus t. And this is the Q and P axis. So for the case of Q, it started at Q0. And to go to QF, what it does, and similarly for the P, it also does something similar. This is for P. Let's take it. This is for P. Okay? So you could see what the system is doing. So it starts, you can start at any point. It very soon actually goes to this point, 0, and remains there because it then doesn't cost it much to be there. But then after a really long time, just near the future time where I want to observe, it just comes out and goes to there. So this kind of justifies what the thing that I use, that I say that I will rather start at Q star and then observe what's the probability at QF. Okay? Because this part, when it came down, it's not it's not very rare. So that doesn't cost much in the large deviation function or in the action. Okay? So this is just an exercise. Okay. Yes, so there's a unique saddle part. So there will be such. Yes, right. Here it's exactly. It's exact. Yeah, right. You're absolutely right. Okay, so let me just now move on. So now just another exercise that I want to leave. So maybe let's erase that part. So I told you in these examples, I solve the problems which are in equilibrium, and that's where I use this property of time reversibility. You can easily cook up examples which are not in equilibrium, and this you can check that the system will not satisfy this time reversibility property. Okay? And I just leave this as the problem. So, as an exercise, it's a very simple problem. You take the same potential, well, but now take two particles. Okay? So here, the potential well is u cubed equal to q square by 2. And I have two particles which are connected by a spring. Okay? So I have q1, q2. So the net energy of the system, q1, q2, the potential energy is half q1 square plus half q2 square plus, so this is very simple case that I'm considering. Okay. Then for this problem, just solve this thing with the assumption that each of these two particles are driven by a different noise. So they have a different temperature. So when you're writing just the Langevin equation, so for Q1, simply again Q1 plus eta 1. So for Q2, it's similar, but just the noise is different. And what you just choose, that when I'm looking at eta I, eta j, it's simply sigma, let's say, I delta ij. So two noises are uncorrelated. So you know that because they're driven by two different kind of temperatures, this would be out of equilibrium. And this problem, you can again solve it. And you should really try to solve it. And then you would see that this time reversibility does not work. Okay. So now I'm going to give one more example. So from now onwards, this course will be mostly solving different examples, okay, with this picture in mind. Okay? And the examples would be more complicated and complex. Okay, so now I'm going to give an example of a out of equilibrium systems where you would find that the large deviation function is non-analytic. And there's something strange happening there, why the non-analyticity is coming, some kind of dynamical phase transition that happens. And you could understand this non-analyticity why in a very simple model. Okay? So let me just come to that. Start. So a bigger version of these non-analyticity and this dynamical phase transitions are actually happens in a much more complicated model. And these are still developing fields, and lots of research papers are written nowadays. But you could see this non-analyticity in a very simple example. Okay. So what is that example? So I'm going to take a system which is on a ring. So it's a periodic system. So I'm going to take the Q variable, which goes from 0 to 1. And then there's, yeah. Precisely. So you can solve both the forward process, backward process, and because it's just a very simple potential, you can actually solve it explicitly. You may need help of Mathematica if you don't want to do so much algebra, but you can solve this problem entirely. Okay, so this is a problem which is, so it's on a ring, so it goes from 0 to 1, and then there is periodicity. Okay? And I'm in a potential, so it's a force which is minus del U del Q. So I'm drawing a potential, so I should have drawn on top of it. Better. Okay, so on this, so I draw the potential. So something like this. So this is U of Q. Okay. If I had only this potential, it would be still in equilibrium. So let's just write down the water vapor in the force for it. Q minus Q. But now to make it non-equilibrium, I add an external force. So what it does, it just keeps on driving in the same direction. What it effectively to do is it will tilt that potential here. What it would do roughly something like this. Okay. But now there is this continuous jump here. So let's call this as V of Q. Okay. And the notation that I'm going to choose that the minima of this blue curve here, call it as Q star. And now V of Q, you can actually write it as integral d of x, f of x, Q star to Q, but for only Q between 1. Okay? So now the question is, in the stationary state, how does the probability distribution look like, and what is the corresponding large deviation function? Okay? So I'm just writing, starting from Q star, and I'm integrating only in this region. So I had this F, Q. Yes, I'm defining. It's not a potential, of course, because there's a discontinuity, but I'm just defining a quantity here, which is just the integral from here to here. It essentially describes this graph with a periodic boundary now. So that's why the non-equilibrium nature, the jump cannot be, so this cannot be like a potential, because then you have a jump and something strange happening. So this is not a potential, and that's where the non-equilibrium nature comes, that you cannot write this force term as a derivative of the potential. Okay, so now the point is that, how does one solve this? So one way is to solve this exactly. Okay? It's just to write the Fokker-Planck equation. Let me remind you, so what would be the Fokker-Planck equation for this problem? So here I'm looking at, for notation, the Lagrange equation, where I'm going to take gamma to be 1. So f of q plus eta, and I told you what I'm doing, eta correlation, simply epsilon delta t minus t prime. I'm also choosing sigma as 1 for this particular problem. Yeah, sorry? Here? So this part was due to the equilibrium potential part. So on top of it, let's say the particle is getting, it's under, let's say, electric field. It's going circle. So let's say it's a charged particle on a ring, and I put a magnetic field. It just goes continuously under a force. So the idea is that it's the force which is constantly driving it along. So that makes it non-equilibrium. Okay? Yes. So for this, F is constant. Sorry. Right? I know. So if you do that U plus FQ, so that's actually is VQ. But what you would have the problem that's with VQ, as you go around, there is a sudden jump. You see, it comes from here to here. No. So the U is the equilibrium potential. Okay. In addition, absolutely, yeah. So this cannot describe. Okay, so that I'm choosing sigma as 1, gamma as 1. I'm going to write down the Fokker-Planck equation, which I have already written yesterday. But this is simply T dq f of q, P, so now it's T of q, T of q, plus epsilon by 2 okay, and then I want to look at the distribution in the stationary state. So I want this to be 0. Okay. So, and in addition, I have this periodicity. So here FQ was such that Q plus 1 should have been F of Q. So this probability also have the same periodicity. So let me give you the solution, which I would leave you to check that it indeed suffices. So P in the stationary state, probability of Q, there is a normalization. And then it goes from 0 to Q dx e to the power twice by epsilon x to q dy f of y plus q to 1 dx twice by epsilon x to q plus 1 dy fy. Okay, so this, please check because I'm not absolutely, I think it's correct, but please confirm that it's indeed true. So everywhere it's period, so it's on a ring, right? So you take any position, add 1 on the coordinate, and you come back to the same position. So the length is just 1. If I start from there, okay, then if I use this property that I want to look at the large deviation function, 1 over epsilon phi of q, so let's say qf. What I want you to again check, that if you put it here, then this phi function, you can actually write it in an explicit form. So let me just write that. Okay. So what I'm choosing also, while deriving this, I'm choosing this v, the v at q star is 0. So I'm just setting this without changing it. Okay. So now you can write down the phi function. It's the following. So phi of q is written in this form. So v of q plus v at 0 minus, so it's written in a bit strange way. So you'll see that the non-analyticity actually comes from here. So range x for v of x, then comma, then v at 0 minus v at 1 plus max, then q x 1 okay. So the idea is that you take this solution, put this form, keep all the leading order terms in 1 over epsilon. For the phi, we'll get that equation. It is a little bit of algebra, but one should get there. If you cannot derive it, just let me know in the tutorial. I will repeat that. Exactly, precisely. You just look at the maximums. So now let's look at how does the large deviation function look like now. Okay? The first thing I want to check, q equal to q star. So I want phi q star to be 0. Right? It's the most probable state. So let's just check that. So what happens at q star? So let me just, okay, I have to jump from there to there, but so at vq star, I told you that we chose vq star to be 0. So the phi q star now becomes twice. So vq star is 0, so it's v 0. Okay. I'm looking at now position q star, so let's just write this twice maximum of, now I have 2 points. So maximum, so I'm looking at the maximum of, in this range, maximum of v in this range where x varies from 0 to q star. So the maximum is the value at 0. Okay. So this is then v of 0. What is here? V of 0 minus v of 1 plus, now I'm looking at the maximum from q star on the right side. It will simply be v of 1. So this 2 cancels. Both are the same, so it's just v0. Okay. And you would see that this would cancel, and you would get a 0. See, it's the maximum of v0 and v0, which is just v0. That cancels with this. So you're still okay. Okay. Now let's look at a point. I need to draw. So I need another. So right now, so now I'm going to erase this part, the white one, and only focus on V. And let's look at this point. Okay. Let's look at a point here. Okay, and let's call that Q of A. And let's look at how that the function looks like. So at QA, so the phi of QA is simply so twice B of QA plus B of 0, okay, minus twice maximum. Okay. So now, if I'm looking at maxima from in this range, it's again V0. So V of 0. Then here's V0 minus V1. Now I'm looking at maxima from in the range from here to there. The maxima would be then here, right? Just do this part algebra, and because you can now just looking at the figure there, you will see that the VQA would cancel from this expression, and what you will get is just simply twice V at 1. So the large deviation function, what would look like here, if I plot the large deviation function, so in this entire region, this part, if I plot now the large deviation function, let's go. This entire region is flat. It would be V at 1. It's twice V at 1. And now you do the same part calculations. Just check from the expression, what would happen, it would simply follow this part. You just use that expression, follow this formula, you will end up looking at a large deviation function which looks like this. So what does it say actually? It says that, you see, you can think about it in terms of path. What it's saying that if I start at this point, I have two ways of going. So I could go this way, or I could come this way. So let's look at the point here. I could come this way, or I could go straight from there. So what would happen if I'm going uphill here? The cost would be roughly this amount of potential. On the other hand, if I go this way, I'll come here, so that's here, then I go downhill. So my cost would be just here. So what's happening, there is a switch of the optimal paths. So as long as you are here, below this point, anywhere here, the path that will contribute is just the shortest path. But then if you are in this region, it's actually the path that will contribute, you go around and come. So there's a transition happening as you move along this queue of this optimal path. It switches. So there is some kind of a dynamical phase transition as one moves from one to the other. Yeah. So I'm looking at the stationary state. So it's a dynamic, so I don't have really kind of a parameter here. So I'm just looking, well, maybe the phase transition is not a good word here. It's just switching between one optimal path to the other as you are changing your position where one is. So maybe that's your parameter. So as you move along this position on the line, and you look at which paths are contributing, you suddenly find that for an entire region, there's a path which contributes, which goes around, and on the other region, it just comes. So I'm not sure whether one could call it a phase transition. So indeed, this picture actually holds when you go to this interacting particle systems. And there are indeed some systems where you'd find that there is a transition from one path to the other. So let me give a reference. So there's a person in Technion. So I know his work. This Yarif Kafri. He is working a lot on this kind of phase transition. They have also written a nice article. So the second author is Bike, I think, Yuju Bike. And I don't remember the exact reference, but it's in JSTAT I think it is 2016, at the very beginning of 2016. Just look at, yeah. 0, yeah. Red is here, this line. Okay. So here to here. Ah. Okay, yes? Okay. Okay, so that you can, I mean, I think we're making some confusion here, but you just sit there and just go through it, you'll find that there's no confusion there. Maybe we do it in the tutorial. Okay. It's a simple, I can go through it, it will just take more time. Well, it depends on how you define, yeah, if you define a measure of the path measure, so that's what actually Yarif does. He relates to the Landau kind of, yeah. True. I mean, if you can define a measure of the distance between two different paths, and in that you can talk about. So yes, so like if you look at TASEP, the example that I said at the very beginning, that there is a rich phase diagram where the full large deviation function is known, and then you have regions which separates between maximum current state and this other low density, high density. That boundary is a second order phase transitions. And there, I guess you would find that. So I have done. Yeah, so that's the large deviation function in phi. So I mean, here I mean in this problem. Right, right. Right. So there, all I'm saying that there is a second order phase transition. You would find there it's a more complicated phase space, but there is a relation to this. One knows the large deviation function, and there is a second order phase transition there. So the discontinuities you would most likely see there. I haven't done this myself, but I believe. Okay, so I need to now, yeah. Yes, so for the time being, I'm restricting myself to the cases where there is a convexity. If it is not convex potential, then something more one has to do. And I don't want to get into that right now. So that I don't know yet immediately. But it's true that as long as this becomes, there's a non-convex potential, something more has to be done, but that needs more discussion. Okay, so let me just, so although this picture that I told you, let me just repeat this picture one more time in the language that we already talked about, which is this Hamiltonian picture. And you will see that this comes out, this particular formula. No, maybe I just skip this because it will take some more time, but roughly the picture is clear right here, that there are two paths which are competing, and then one goes from the other. In the tutorial, I could do the same exercise in the Hamiltonian picture when you calculate really solve the minimal action paths, and you would really see that there is a transition from the optimal path that one gets. It's very simple to solve that problem, but let's now move to another problem. Okay, so the one most property that I want to mention. So I told you that when I'm looking at the stationary state problem, the paths that contribute, they are associated to the Hamiltonian being 0. Okay? So where does that come from? So it simply comes from this, you can understand this, from this picture called Hamilton-Jacobi. So again, this is a very standard thing in classical mechanics. I'm not going to derive things. You can look at references like this classical mechanics book I very much like. It's an Indian edition. And there is a very nice lecture notes by David Tong, in Cambridge. And you will find these discussions there in the classical mechanics. Okay? So what does it mean that, so essentially what we were doing is we're minimizing the action, right? So we wanted to look at, say, at time t, I want to be at position f. I had this path integral over p and q, and I had 1 epsilon s of p and q. And then I said that this has this large deviation function from epsilon phi of qf, and now it will depend on t because I'm looking at the position at time t. And this is nothing but the minimal of the action. Okay? So this is S min. Okay? Now, in classical mechanics, one does this canonical transformation to solve this minimal least action problem and make a canonical transformation where one could directly write an equation for this minimal action. Okay? And you all know that how that equation look like. So if I write, so the minimal is exactly the same as the phi. So let me just write that equation in terms of the phi. So it would be dt phi at qf at t is equal to minus h. So h was the Hamiltonian, effective Hamiltonian that was in the action. So in place of p, all I write is del phi del q of f, then replace q of f. Okay, so let's just look at this equation. This is known as the Hamilton-Jacobi equation in classical mechanics, and I believe most of you have seen it. So what it's doing, that I'm just writing a time evolution equation of this large deviation function now. So it's the given at position qf at time t. So that time evolution is nothing but minus h, where I replace p by del phi del qf. The q I replace by the final position qf. Okay, so as an exercise, do the following. Take the Hamiltonian that appeared in the problem where we had f was minus del u del q. Okay. Now, if I want to go in the stationary state, all I have to do is put this term to 0. So the check that the equation that you would find for the case of this following problem, the stationary large deviation function for this potential, check that that large deviation function which we found, which was simply so phi qf is equal to u of qf divided by kt. It satisfies the equation, this equation, the stationary state. Now, as I told you that in the stationary state, we find this h equal to 0, and you immediately see this coming from this part, that in the stationary state is essentially h is 0. It's not a very good answer, but it's one reason. Okay? Okay, so let's solve another problem now. Now, this problem that I want to introduce is to introduce a concept which is called additivity principle. Okay? So this additivity principle was first introduced by Bernard and Thierry Boudinot in order to solve the large deviation function for current profile. So the currents that I wrote at the very beginning examples. Okay? So that problem is quite complicated, and I will discuss that problem maybe in the last lecture. But today, in this very simple Langevin equation case, you can see that that additivity principle one could understand in this problem. Okay? So for that, I will look now at an observable, which is kind of equivalent to the current. So it's not really current, but I'm just going to cook up an observable where one could see this additivity principle. Okay. So this is what you will find that from the lecture, in the last 2 lectures where I will discuss this fluctuating hydrodynamics and so it depends on how you define the current, okay, in this Langevin equations. Yes, indeed one could do that, but I'm going to take an observable which is not exactly current, but essentially in the analysis, it plays a similar role. Okay? So which is nothing but the area under this trajectory. So I'm going to now look at, so keep in mind, so the motivation is we want to understand additivity principle in this very simple problem, which will appear in the last lecture. So I'm going to look at now a quantity, which is Q of t, that's starting, so Q0 t. So it's the area under the curve. Right? So you could see that this is a highly non-local property. It is rather difficult to solve, but you'll see that this problem, using additivity principle, one could solve in just few lines, 2-3 lines. But first, I will try to solve it in a bit lengthier way to convince you what is the reason behind additivity principle. So I'm now looking at this exactly the same problem, f of q plus eta, with eta is simply epsilon delta t minus t prime. So all the gamma and sigma, I took it as 1. True. So here I am considering f of q is again just the derivative of a potential. Okay? But for the timing, I'll just keep the f of q here. True, it would depend on, yeah. But you already saw that for the case of the position, even I have chosen f of q in a non-equilibrium way, there was a large deviation form there. Right? Yeah, so then it just goes to infinity, so I just wanted to bound it in a place so that, yeah. So under those kind of properties, that it has to be confined in a place, it should not just divert to the infinity. True, absolutely true. So absolutely true. So let's just go on the calculation, still keeping f of q, and then we could see what are the criteria one may need. Okay? So now what I'm going to do is just going to look at this generating function. Okay, so the property that we would like to study is what is the probability. So right now I'm not considering t to be very large. Okay? What I want to study, is there a large deviation form like this for this problem? T is still not large. Only assumption is that epsilon is very small. Okay, so now what we want to do, I want to look at this generating function. So lambda of qt, then I put a 1 over epsilon here. Now why is that? Because then if I take a log of it, and if I kind of assume that there is this large deviation form, then this would simply be, so there would be log, then d of qt, e to the power lambda by epsilon, and then I have just qt, I use this form here, dt to t, q of t, minus phi of, sorry, I don't need it here. I'm sorry. Still keep it. Okay. And then you know that if this quantity in this saddle point, it would be something like epsilon, then the maxima of this quantity. So let's just write that as g lambda, which is simply 1 over epsilon maximum over qt lambda qt minus phi of qt. The reason is now that if I know g lambda, I take the reverse Legendre transform, which would simply be that phi of qt is again maximum over lambda qt minus g of lambda. Okay, so this is what we want to do. First, I want to calculate this quantity. Okay. So it's quite straightforward. Now you all know how to do this. So I'm just going to look at lambda over epsilon t. Now I have the action formulation, so P of Q, e to the power lambda over epsilon, and I have T is 0 to T, Q of T, minus the action. So this is dt, 0 to T, 1 over epsilon, and I'm going to write it in the Hamiltonian form, T minus H of PQ. Okay? Okay, so this, now you could just redefine as same thing, it's just for simplicity. You can write it as just 1 over epsilon action, PQ, where S PQ is, I'm just repeating this thing, but it's good something. So what I'm going to do now, take this term and absorb in the Hamiltonian. So this now is a different. So now let me write down the explicit form. P square by 2, I chose sigma and gamma to be 1. So this is the original Hamiltonian, and to that I'm adding. Okay. Essentially, again, the same picture, I want to calculate the minimal of the action. That will give me my G lambda. And from G lambda, I'll take a Legendre transform, I'll get the phi. And we'll see now how this additivity principle comes. Okay, so this is one exercise. I want to do it really step by step, because later on, I will not repeat this kind of calculation. So what I want to do now, I want to calculate the minimal of the action. Okay. So for that, I just need to do a variational calculus. So this now, we want to look at if I change P by P plus delta P, Q by Q plus delta Q, the action will change accordingly. And let that small infinitesimal change in action is delta S. Okay? And we want to find out what is that infinitesimal change. And around the minimal action part, this change should be 0. Right? So this is one part. I'm going to do it a bit carefully so that later on you can. So what I'm going to write down this part as dt. The small change that the delta S would have been delta. So first, let's look at all the terms that will change due to P plus delta P. So this term would change. The change would be delta P times Q dot. There would be a change also coming in from the H. So that would be delta P, delta H, delta P. Okay. So let's just write down. Let's look at what is the contribution that would come from change in delta Q. So that, I just write P, so d dt of delta Q. It's coming from here. So I'm changing Q plus delta Q. I'm looking at the contribution to the linear order. So this is P d dt of delta Q. And the change in H is delta H, delta Q, delta Q. Okay. You see that, why am I doing this? Because it would be important for the boundary conditions. Now what do I do with this term? You just do an integration by parts. Okay. So if I do an integration by parts, there will be one term which would be like dt, then ddt of P delta Q, minus dt P dot delta Q. Right? Just an integration by parts. So I take this, write it here, change the sign, it will simply be this part, only keeping this part. It would be P dot delta Q. I take this thing out here, delta Q. Okay. I still have this part, so I just leave it there. So this is P, so this is an integration total derivative, so it would be P at capital T, delta Q at capital T, minus P at 0, delta Q at 0. Right. Yeah, absolutely. Absolutely. So we are minimizing over this new action. The reason I did this exercise bits in details is to see where does this boundary conditions in the optimal fields comes from. Okay? The first thing you note that if I now want this to be the minimal of the action, this has to be 0. So clearly, for this to happen for any arbitrary change of P and Q, this is delta P delta Q, this term has to be 0, and this term has to be 0. This too will give you the Hamilton's equation that I wrote before. In the previous problem, the boundary conditions was that I fix my initial position and also the final position. So Q at capital T was fixed, so I cannot change this. The delta Q was 0 by default. So this contributed 0. Similarly for the initial. But now I'm looking at a different problem, which is the problem for this current. So the problem was that which I did not state probably this part, that I want to look at the probability of seeing this QT. Well, let's say I start at Q0 being 0. Okay. Let's say I fix the initial position. So that will take care of this. But I'm not fixing my final point. So for that, then I need this term to be 0. So for that, I need a boundary condition that PT has to be 0. You see, now the boundary condition for this problem is different. So often you would find that this kind of problems, at least in the interacting particle systems, there would be almost same bulk equations, but depending on which observable one wants to look at, or the statistical properties, the boundary conditions would be different. Okay? The next time onwards, I will not do these derivations. I'll simply give the boundary conditions, but you could go back and do the same calculation, and you'll find this. So now for this problem, what we ended up. So now, what the problem now reduced is that now I have Q dot, I have to solve this problem. So H wiggle. This is simply P plus F of Q. P dot is equal to minus delta wiggle delta Q minus P F prime of Q minus lambda. Okay. With the boundary condition that Q of 0 is 0 and P at T is 0. Okay. And now what I want is the minimal action, which will give me G of lambda, which is the S min. Okay. What you do is just take this equation, put it here, replace what Q dot. You'll find that this expression just simplifies a little bit. So I'm sorry, I'm just doing all these algebra details, but at least in one example, I want to see what's really going on. Okay? Rest would be very similar kind of idea. No, so what's happening that whichever boundary condition I put, or the problem that I want to see, there is a correlated noise path, right? I mean, and it turns out that, so I don't have a very good answer to that, but it turns out that if I want this to be minimum, then the correlated noise comes out in a way that at the boundary, the P has to be 0. I don't know if there is a physical meaning to it. Probably there is, but I don't know yet. But it's just the fact that I want to see a particular profile with these boundary conditions. So the P is already determined by this noise history, which is contributing. And it comes out by automatically from this analysis, that one needs that. Maybe there is a better explanation to this. Okay, so far, then this is what happened, right? So the G lambda, just this, I have to just solve these equations with these boundary conditions, and I would get G lambda. Okay? So all problem just reduced to this. Okay? In general, it would be difficult to solve this problem for any f of q. Okay? Let's just solve for the case, which is very simple, and our favorite one, which is this harmonic well. So I'm writing uq is equal to half q square. This means f of q is equal to minus of q. This is the derivative. So let's see what happens in this problem. Okay? Okay. So this case, you could easily solve. If you solve it, let me just write down the solution. Lambda 1 minus or minus t minus so capital T is up to the time I want to see, with t minus e to the power minus t, and p of t 1 minus e to the power minus capital T. Okay. Now let's just plot it. Is there any question? So if there is any part which is not clear, just let me know now or later, because later from the next 2 lectures, it would be more involved problems. Okay? But the basic ideas will still remain the same. So I'm plotting here q of t. This part is lambda. And if you plot it, I started at q0, goes here, remains there, and somewhere towards the end, it just comes down. If I plot the p, now it's the p of t. It started at lambda, goes there, and very towards the end, it comes to 0. From this, you can just see. So what it says that most of the time, the optimal profile just remain constant over time. Okay? So for this problem, this is almost the additivity principle, says in this particular problem, the optimal profile, the contribution that it comes from, it was time independent, both in P and Q. Okay? So if this is true, then if I want to now look at the problem for very large T, okay, I could just simply ignore these 2 parts, because in this time integral, they're almost negligible contribution. So then what I could do, I simply replace this. Okay? So I have dt, so it's roughly. So I'm saying that P and Q are constant the most of the time, so this would give me a factor T. P remained at lambda, so it's lambda square by 2, minus lambda. Q also remained at lambda square. So this is simply T lambda square by 2. Okay. So if I'm looking at the problem now in a little redefined way, that now I want to look at the large deviation of the quantity at a very large time, then it just simply reduced to the problem of solving the case where the optimal profile is constant. Okay? And there I have this similar large deviation form, okay, where it turns out now the G lambda is proportional to T. All I now do is I want to look at the large deviation function, I put the formula of G lambda here, and I take the Legendre transform. Very simple algebra. What you will find, so this is all in the large T limit. All that one would find, phi of qt, t by 2. I'm just going to write it in this way. You just have to take that formula, put it in this form, take the Legendre transform, you'll get that. So in this case, So what would now happen, so what I'm now going to write, this large division form, in a little different way, because I see that it is a function of qt by t if I have the prefactor t. Okay? So I'm just going to rewrite this large deviation form. Simply. So now if I'm looking at the problem at large capital T, I want to look at qt by t, call it r. This would go as e to the power minus t by epsilon phi of r, where for this harmonic well, this potential well, it is simply r square by 2. Okay? And it turns out that this is also true for any f that you take, given certain conditions. Okay? But it works in a more general setup. So you see that this is r square by 2, and if you look at the potential here, so f was minus q. So because I already know the answer, I'm just going to write this as half fr whole square. The claim is the following now. So let me just write it cleanly. The claim is, under certain conditions on the function f, the potential, what one would find that if I'm looking at the quantity of this integrated value at large T, it has this following large deviation form, where phi of r is simply half f of r whole square. Now, I'm going to give an argument why this happens in just 2 lines, starting from this Lagrange picture. Using this, so now if you use additivity principle, the fact that in the large time case, the optimal profile that you find is time independent, then you would get this answer really fast. So what I'm now interested in, the question, now I want qt by t to be r. Okay. So this came from, so I'm now in the Lagrange picture. Okay. Minus 1 over epsilon 0 to t dt q dot minus f of q divided by 2. Okay. Now in the large time limit, it's the profile that contributes mostly is the time independent, so q dot is 0. This would simply give you fq square. The time just gives you a factor. Now what was q? Is I want dt 0 to t q of t. This I want as t times r, and I'm claiming that it comes from a time independent profile. So what would only be that the q is just r. So then that gives you. So this particular concept that you used in this very simple problem actually helped to derive, probably for the first example, that for any arbitrary diffusive systems, one could derive the exact formula for the large deviation of current. So this is in a paper, I will give the reference later on. Okay, so I want to look at this probability. Okay. So my action formulation was just e to the power minus 1 over epsilon, and then there is Lagrangian. Then I know that for this epsilon small limit, is the minimal action which would contribute. Now the additivity principle says that the minimal action, the paths that it contributed to it, is time independent. So then in the formula, I just put q dot equal to 0. Then it simply becomes f of q whole square by 2 with a prefactor t. What was that q? It's because you see I wanted this to be TR. For large time, the time independent part is just R. It is simply then T by epsilon FR whole square by 2. Okay. So this paper's reference I will give later, but it's by Derrida. It's a PRL 2004. So if you go to the website of Bernard Derrida, he has a really exhaustive list of all his publications, tabulated under every year. In 2004, you can find this article. But that was for more in an interacting particle systems, for more complicated problem. They are to study the statistics of current fluctuations, the net flow of particles. And using this simple additivity principle idea, one could solve that problem really fast in just few lines. And you would get an expression for this large deviation of current for almost a general class of driven diffusive systems. Like I will talk about what are the special criteria, but it was solved for a really large class of systems there. Okay? So the next lecture, what I'll do now, I'll go into the actual macroscopic fluctuation theory, which is about this fluctuating hydrodynamics of interacting particle systems. So far in all these 3 lectures, what I wanted to do is to give you an idea what goes behind this kind of approach. You need to do some kind of field theory, and then you just calculate the minimal of the action. Now, when we go to this fluctuating hydrodynamics, it would be a little more involved. I will not do all the algebras. I'll try to skip some parts, but the basic idea would remain the same. So today, the reason I went through all these things in details, I wanted to make sure that you understand every step. And if it is some parts are still not clear, please ask me today. So tomorrow onwards, it will be more involved problems, but there I will not do all the algebras. So it's true that in this case, you could have scaled your coordinates with a capital T, and then you could have done it. You wouldn't have needed the epsilon small. Okay. But if you are thinking, it would be, so you would have to just rescale. So you would just, the epsilon would just go away. You see, in this large deviation function, you could simply talk, even in the case where the noise is not weak, you just make epsilon 1, but you now have to talk about really large T, and then you would have still that large distribution. Right. Yes, so that's exactly the case. So small noise strength will take longer time to make certain effect. So this is actually what I will do when we are in the fluctuating hydrodynamics. I will not put any small parameter by hand. Sometimes you would just see that I will do scaling with the total time, and sometimes with the system size. And there the smallness will come out quite naturally, and there are reasons why it comes.